Vaishnavi, and today I'm excited to walk you through my reinforcement learning project. What you are seeing on the screen right now is an autonomous AI agent navigating a track completely on its own. The car isn't following a hard coded path, and there are no if else rules telling it how to drive. Instead, it learned how to steer, accelerate, and brake through trial and error using a reinforcement learning algorithm called Proximal Policy Optimization or PPO. To build this system, I created a custom 2D driving simulation using Pygame, designed a gymnasium environment for reinforcement learning, and trained an AI agent using a stable baseline 3 and PyTorch. In this video, I will take you under the hood and explain how the system perceives the environment, make decisions, and learn to drive autonomously. The first major challenge was building a reinforcement learning environment that follows the Gymnasium API standard. Reinforcement learning libraries require environment to provide structured inputs and outputs. So I have created a custom environment called Car Racing ENV, which is a car racing environment which inherits from the base class Gymnasium environment. Inside this environment, I define two critical components: the action, the action space, and an observation space. The action space defines what the agent is allowed to do. In this project, the action space is a discrete set of 5 actions at any given moment. The AI can choose what action to perform. It's like you can either do nothing, accelerate, brake, turn left, turn right, etc. These actions are executed many times per second during the training. But the next question is, how does the agent actually sees the track? Yep. In real world autonomous vehicles, perception is often handled using LiDAR sensors that measure distance to a nearby objects. To stimulate this effectively or efficiently, I have implemented a custom ray casting system. The car fires 5 invisible sensor rays outward from its front side across an arc. Inside the catch ray function, each ray is mathematically extended outward until it interacts or intersects with a wall in the track. When a ray hits a wall, an algorithm calculates the exact distance from the car to that wall. These distances values act as a car's perception system. So instead of seeing the pixels, the neural network receives a simple numerical input like I am moving at an x speed of x. There is a wall 20 pixels to my left and 150 pixels straight ahead and 80 pixels to my right. These 5 sensor distances plus the current velocity from the 6 dimensional observation vector that AI uses to make the decision. In reinforcement learning, the agent improves its behavior purely based on rewards and penalties. Designing the reward function called the reward shaping is one of the most important parts of the entire project. Inside the environment step function, the reward system encourages the agent to drive properly. First, if the car collides with a wall, it receives a large penalty of minus 10 points and the episode ends immediately. Second, the agent receives a small negative penalty every time step. This prevents it from staying still and encourages it to move efficiently. Finally, the agent receives a positive reward proportional to its forward velocity. The faster it drives without crashing, the more reward it gets. Over thousands of episodes, the agent gradually learns that safe forward motion leads to the highest rewards. Once the environment was ready, I trained the agent using a stable baseline 3, a highly optimized reinforcement learning library. The algorithm used here is a Proximal Policy Optimization or PPO, which is widely used for continuous control tasks. I've used an MLP policy which stands for multi-layer perceptron because the observation space is a simple numerical vector rather than a large image data. The neural network lightweight and can train efficiently even on a standard CPU. Training runs for 100,000 time steps during which the agent repeatedly interacts with the environment, collects the rewards, and updates the neural network weights to improve its driving strategy. To track performance, I have implemented logging the records the agents mean reward over time, which allows us to visualize how learning progresses. This graph shows the reward curve over the training period. The beginning of the training, the car behaves randomly. It often accelerates directly into walls, producing negative rewards. But as training continues and the neural network learns from the experiences, we can clearly see that there is an improvement. The reward steadily increases as the agent learns how to, avoid collisions, maintain forward speed, navigate the track effectively. Eventually, the reward curve stabilizes, indicating that the agent has learned a reliable driving strategy. Finally, by the end of the training, the agent successfully learns how to drive around the track. As you can see in the demonstration, the car smoothly navigates the environment, maintaining a speed, avoiding collisions. It understands when to steer into corners and when to accelerate along the straight segment of the track. What's remarkable is that this behavior was not programmed manually. Instead, the agent discovered this driving strategy entirely through trial and error interaction with the environment. To summarize the project demonstration, a complete reinforcement for learning pipeline is that first, a custom Pygame stimulation was built to represent the driving environment. Second, the stimulation was wrapped into a gymnasium reinforcement learning environment. Third, a sensor based perception system using array casting was implemented. Finally, an AI agent was trained using the PPO algorithm from stable baselines 3. The entire project is containerized using Docker, making it easy to reproduce and run on any system. Thank you so much for watching. And if you are interested in exploring the code or running the simulation myself, the full project is available on my GitHub repository. Thank you for watching.